Hello, my dear students, and welcome back. We're still working with Chapter 8 from our Calculus 2 course. We're done with Section 8.1 about sequences of real numbers. Today we'll move to infinite series. The plan for this chapter from 8.2 to 8.8, you're going to learn some well-known series, which I'd call it like famous series that you have to recognize. And you will learn a good number of tests you use to check whether any series is convergent or divergent. Basically, for this section 8.2, you will learn 3 famous series and 1 test to check for convergence. Now, firstly, we need to understand what do we mean by series and what's its relation with our previous section sequences. So when we talk about sequences, just as in section 8.1, we have a list of terms, okay? Just like A1, A2, you keep going up to, you have infinitely many terms. We used to write it last time either by listing the terms or you use this notation. So AK as K going from 1 to infinity. Now let's say that for the terms of sequence, we start to add up its terms. And we use the notation which we call the partial sum. We use the partial sums. Now for the partial sums, if I start with S1, which is the first term, and then I move to S2 and I add up the first 2 terms, which is basically S1 plus A2, then S3, you add the first 3 terms, which is S2 plus A3, and you keep doing the same thing up to, in general, to Sn. So I'm finding the partial sum for Sn. You add up the terms for the sequence from A1 up to An. I could see it as Sn minus 1 plus An. So just like every time you add up one additional term. This is what we call the partial sums. Okay, this is one thing. So now we know we build up our partial sums on adding up the terms of a sequence. Now, for example, if I think about this sequence 1 over 2 to the power of k, and we took k from 1 to infinity. Now once I keep adding, okay, I keep adding these terms with the partial sums, and I take the limit of this sequence of the partial sum, okay, we'll take the limit of the partial sum, so it should be something similar to this. So in general, these are the sequence. So if I take the limit for Sn as n approaches to infinity, I could write it as limit of Sn, we know it's sigma k equals to 1 up to n as n approaches to infinity. For this example, it's 1 over 2 to the power of k. So basically, it's not the normal summation. It's just like you're finding the limit of the partial sums as n approaches to infinity, okay? So this is Sn. The summation that we found already in the previous slide. We add up from S1 to infinity to n, and then we take the limit for this summation as n approaches to infinity from 1 over 2 to the power of k. We'll see later that this one will be equals to 1. It's coming. Now, this is what we call a series or infinite series. Okay, they have the name infinite because it goes up to infinity. Now, in general, see, this is the first official definition that we have for infinite series. So we say that if we have the partial sum Sn as sigma ak from k equals to 1 to n, and we say that this sigma converges to some number, let's say it to s, we can say that this sigma, it's equal to limit, just as I did in the previous slide. So it's the limit for n approaches to infinity from 1 to n, and we say this is equals to s. If this limit exists and it's equals to s, so we can say that this series is convergent to s. If not, if the limit does not exist, so this series is divergent. Okay? So what we need to do, we need just to write Sn, the partial sum up to n, and then we take the limit as n approaches to infinity to check whether it's convergent or divergent. Okay, let's move ahead. See what do we have next. Now this is our first example. We need just to think about series. How do we see series? This first question or first example, it says what? You need to investigate the convergence or divergence of the series sigma k squared from k equals to 1 to infinity. It's always very useful approach to do what? List some terms, okay? It's always with any series, try to list some terms, try to expand this. Just see few terms of this summation. How do I find the terms? If k is equals to 1, so it's 1 squared, plus k equals to 2, so this is 2 squared, k equals to 3, so this is 3 squared, then 4 squared, then 5 squared. So if you think of this, this is a series of the summation of square numbers. So you're adding up 1 plus 4 plus 9 plus 16 plus 25, all perfect square numbers. I'm adding them up. So if you think about this summation, it's going to where? So if I'm thinking about the limit for sigma from k equals to 1 to n for k squared, as n approaches to infinity, I'll think about it as it's getting bigger, bigger, bigger without a bound. So if I add all of these numbers, the limit will be equals to what? Infinity, for sure. This limit will be add up to infinity. So I can say that the limit does not exist. Limit does not exist. So hence the series diverges. Okay? It's clear. Just think about it. Does it go anywhere? If I keep adding up the values, what will happen? It's getting bigger, bigger, bigger. So this is a good example of divergence series. If you think even, this is for you just to think about it. If you think about very simple example, something like this. If you have sigma for only k, you're adding up integer numbers from k equals 1 to infinity. This is again would be what? Another example of divergence series. Okay, let's see what do we have next now. This is a solution for the same question. Now we'll start working with, we understand what do we mean by a series. We know it as a summation of all partial sums of sequence. Now we'll start with one of the famous series I told you about, what we call telescoping series. This is really interesting type of series. This series, if you try to expand the terms, okay, and check what's the partial sum, you'll notice that most of the terms will be cancelled out. That's why they call it the collapsing sum. Most of the terms will be cancelled out except a few. Sometimes the first few terms or the last few terms. So you end up with a finite number of terms. So it will be convergence to these values. So we need to check. It will be equals to what? And how can we see the pattern of cancellation? How can you check? What you need to do basically is you need just to list these terms. You have to check few terms at the beginning, few terms at the end, and see the pattern, what's happening, what's cancelling out, what's remaining, okay? So this series is what we call telescoping series. What's the general form of the telescoping series? Usually it looks something like this. So you have the sigma from, let's say, k equals to 1 to infinity. So it looks like, let's say, bk minus bk plus 1. So what always you see with telescoping series is the negative sign in between. This is fundamental. It should be always negative in between. And subtraction of two similar functions. So it could be exponential minus exponential, tan inverse minus tan inverse, rational function minus rational function. Okay, so they should be from the same type, sine minus sine. Most of the examples that you'll see in your textbook, they are about rational functions, okay, which we need to use partial fraction decomposition. Remember, as our section before, dealing with partial fractions. So most of the question where you need to use partial fractions, it could be a good candidate for telescoping series. Something like this. Let's start with the first. I added a good number of examples for telescoping series. Something like this. You see, once you see this question, it should always remind you of the partial fractions. So 1 over k times k plus 1. So if I need to do it as partial fractions, I need to prepare first, okay? I need to do just what you covered in the previous chapters. So if I start with just to do the partial fractions, I'll start with 1 over k plus 1. Notice this is the case where we have two distinct factors, both of them linear. So I could write it as a over k plus b over k plus 1. Then the next step, remember, this is your LCD. We start with 1, the numerator, equals. We always do what? You keep, this is the LCD, the least common denominator. So we start with a, just to have the common denominator, just like you're multiplying the whole equation by k times k plus 1. So a times k plus 1, so you have a k plus 1. You always can do it fast by looking at the LCD and multiply by the missing part of the denominator. Plus b, there's k plus 1, what's missing out of the LCD? It's k, so that's the equation. Now I need to solve this equation to find a and b. The easiest way to do it here, remember we did two different methods. Either you take values for k, so let's say I'll take k as equal to -1. I'll take the zeros, it's the easiest one for calculation. If k equals -1, so this is 1 equals, this term will be 0 and this will be -b. So basically you'll have b as -1. Now the next time you can take k as 0. So if k is equal to 0, so this is 1 equals 0 plus 1, 1a, and this term will be 0, so a equals to 1. So this is what we have. A equals to 1, b equals to -1. So to work with this question, you need to add one additional step at the beginning. You need to prepare the partial fractions. You need to work with partial fractions. Okay, so now the question itself is equals a is equal to 1 over k minus 1 over k plus 1. Perfect. So now this is what we have. We prepared the partial fractions. Now, if you look here, it fits what we talked about before. There's minus in between. This is not always plus 1, but there's a difference between them. So there's a minus in between, and both of them, they are the same type of function. 1 over k plus 1. Okay, now the next step will be, we'll try to find or to see the pattern when we expand this summation. So see, we'll continue in the next slide. So now our question is what? Sn equals sigma from k equals to 1 to n, and the two fractions we had as 1 over k minus 1 over k plus 1. This is our starting point. Now what do I need to do? I need to expand some terms. This is equals, replace k with 1, okay? Start expanding. This is the easiest way to do it. So I start with, if k is equal to 1, k equals to 2, let's take few terms. 3, k equals to 4. Let's see what do we get. If k is equal to 1, 1 over 1, 1, minus k equals to 1, 1 over 1 plus 1, 2. So this is half. In between, it will be plus. I'll do k equals to 2, 1 over 2, half, minus. Here 2, it's 1 over 3. We'll move to k equals to 3. You see, it's always plus in between when I add up the expansion because it's a summation. This is k equals to 1. Okay, to 3. Now I think the pattern is clear. 1 over 3 minus the next number 1 over 4. And then plus 1 over 4 minus 1 over 5. And you keep going on the same way. Now I need the last few terms also. Plus, we keep moving. I need the last few terms. What could be the last term? Notice that we add up to n. So the last term could be k equals to n. The one before should be k equals n minus 1. Okay? It's enough. I'll take the last two only. So now as k equals to n minus 1, let's do this one. K equals to n minus 1. 1 over n minus 1 over n plus 1. For k equals to n, it's 1 over n minus, this is n minus 1, sorry. So this is n minus 1, this is n, and this is 1 over n plus 1. Okay. I think this is a good number of terms. No need to add some more. Now see the pattern. What's happening here? We took few terms at the beginning. We took few terms at the end. Now, if you keep looking here, what do you see? The second one will be cancelled with this. Half with negative half. 1/3 with negative 1/3. Negative 1/4 with 1/4. If I write the next one, for sure it will be 1 over 5. This will be cancelled. Everything will be cancelled out. At the end, at the tail of this series, what's happening? Minus 1 over n will cancel with 1 over n. The one before, for sure, it was going to be minus 1 over n. It will be cancelled. So what will be left in this case? Only the first and the last. This is the only terms left. Okay. So now the summation equals to what? Sn equals 1 minus 1 over n plus 1 only. That's why they call it the telescoping series, because all the terms collapse except only the first and the last. Okay, and usually you expand to see just few terms till you see the pattern. You can decide what do you cancel out. So now the next step should be what? I'll take the limit for Sn as n approaches to infinity, and this is equals to, if you take the limit for this part, 1 minus 1 over n plus 1 as n approaches to infinity, and this is clearly equals to 1. So I can say that hence the series converges to 1. Converges to 1. Okay, this is the long way to do it. Now I'll teach you how to do this in a faster method. Something easier, no need to expand a lot. I'll teach you what to do. Now the fast method depends on what? You need always to look at the original question with the negative sign in between. You see what's the difference here? From k to go to k plus 1, what should be the difference? It's only 1, okay? Think about here. To go from k to k plus 1, the difference is only 1. So how can this 1 be useful for me? If the difference is 1, so I know I will keep one term at the beginning, the first part, and one term at the end. One term at the beginning and one term at the end. Okay, this is really useful. It helps me to do it super fast. Okay, if the difference is 2, I know that I'll keep 2 terms at the beginning, 2 terms at the end. Not necessarily the first one or the last one, but at the first part. From the first part, I'll keep 2. At the last part, I'll keep 2. Now, in the next few questions, we'll try to follow this faster technique. Okay, let's check one more. This question, we need to find the whether this series is convergent or divergent. Now, the first step, I've done it already for you. So the question originally looks something like this. So anytime you see a question which should remind you of the partial fractions, you have to do the one additional step at the beginning. So if you do the partial fraction, it will be written as 1 over k plus 1 minus 1 over k plus 3. Now the technique, the faster one. So what's the difference between k plus 1 and k plus 3? The difference from here to here. How do I go from k plus 1 to k plus 3? Clearly, it's plus 2. If it's plus 2, that means I'll keep 2 terms at the beginning, 2 terms at the end. Okay, it's good. So I'll write the first 2 terms. Now I need Sn. Remember, we don't take it up to infinity. We need only up to n first. Then you take the limit. So this is Sn from k equals to 1 to n for 1 over k plus 1 minus 1 over k plus 3. Now, this is the trick. You need to take the first 2 terms. Okay, I'll take the first 2 terms. 1 over k, now it's at k equals to 1. K equals to 2. At k equals to 1, it's half minus 1 over 4. K equals to 2, it's 1 over 3 minus 1 over 5. Then I'll stop, only the first 2 terms. Now I'll find the last 2 terms. So at k equals to n minus 1, the last one, k equals to n. At n minus 1, what should be the term? Replace k with n minus 1, okay? Just substitution. N minus 1 plus 1, it's 1 over n. Minus n minus 1 plus a 3. N minus 1 plus a 3. So this is n plus 2. The last term at n, 1 over n plus 1 minus 1 over n plus 3. Okay, this is enough. No need for more terms. Now what should be left? Okay, what should be left? What can we cancel out? The terms where you need to keep, think about it this way. The first 2 positive terms. So this one will remain. And the last 2 negative terms. This one and this one. Else everything will be cancelled out. Okay, no need to expand more, even though you don't see it now as you cancel out terms. But trust me, if you add one more at k equals to 3, so you'll have like 1 over 4 minus 1 over 6. The next one, it will be 1 over, at 4, 1 over 5 minus 1 over 6. Okay, so it's coming. You're going to cancel it out eventually. But no need to show all the additional terms. So I know if the difference is 2, I'll keep the first. So you keep the first 2 positive terms. 2 positive terms. And the last 2 negative terms. This is if the difference is 2. You keep the first 2, you keep the last 2. Okay? So now what should be Sn in this case? Half plus 1 over 3 minus 1 over n plus 2 minus 1 over n plus 3. Take the limit for Sn. As n approaches to infinity, it equals the limit of half plus 1 over 3 minus 1 over n plus 2 minus 1 over n plus 3 as n approaches to infinity. And these 2 will be cancelled out with 0, and you end up with half plus 1 over 3, and this is equals to 5 over 6. So we can easily say that this sequence converges to 5 over 6. So this is converges to 5 over 6. This is our final conclusion. Okay, clear the idea? So this hint is really useful. Else you need to expand really sometimes a lot, like 4 or 5 terms to see from the beginning at the end, to see the pattern, what's happening, what do you cancel, what do you keep. Okay. Now let's try one additional question. Try one more. Now, this is different style. The first two examples were something that you use the partial fractions. Now this one is different. Still, we're saying just what? I see negative sign in between. You see, how do I guess? Is it possible to be telescoping? There's negative sign in between, and the two functions I'm subtract here are from the same family. So e to the power of 1 over k, e to the power of 1 over k plus 2, they looks almost the same function. Now, if you look at the difference, you think about the difference in between. So what's the difference between k and k plus 2? Clearly here, again, I add 2. I added 2. Okay, let's do it. So we start with Sn equals sigma k equals to 1 up to n for 1 for e to the power of 1 over k minus e to the power of 1 over k plus 2. So I need to find what? The first two terms. How do I find the first two terms? When k equals to 1, k equals to 2. Okay, let's do that. Replace k with 1. So this is e to the power 1 over 1. It's e to the power of 1. Minus e k1. So it's 1 over 3. This is the first term. Move to the second one as k equal to 2. E to the power of half minus e to the power of, you add 2 always. So it's 1 over 4. We'll keep adding. Now I need the last two terms as well. So you add, now I need k equals n minus 1 and k equals to n, the last two terms. Okay, fine. The one before the last, so this is e to the power 1 over n minus 1. The one after, it's e to the power n minus 1 plus 2, so 1 over n plus 1. The last one at n, e to the power 1 over n minus e 1 over n plus 2. Okay, that's it. I'll stop now. Now I know that all the terms will be cancelled out except what? The difference is 2. So I'll keep the first two positive. You notice, not the first two terms. This is important. Not the first two terms. The first two positive terms. So this one. And the last, just like you replace the first one, the first function, the first two values for the first function. And the last two negative terms, which is this one. Else it will be cancelled out. So this is equals to, what will be left here as Sn, we'll have e minus e to the power 1 over 3 minus e 1 over n plus 1 minus e 1 over to the power 1 over n plus 2. Now I'll take the limit as n approaches to infinity for e to the power of 1 minus e power 1 over 3, 1 over n plus 1, 1 over n plus 2. Now take the limit. Remember, with limit, you need always to start with direct substitution. Try to do the direct substitution. This is e to the power of 1 minus e to the power of 1 over 3 minus 1 over infinity, it's 0. So this is e to the power of 0. Okay? And this one is the same, e to the power of 0, which is equal to 1. So this is minus 1, minus 1. So this is e plus or minus plus this one. The first one, this is, I took the first two, this is half. This is positive, this is positive. So this is positive half, okay, minus 1, so it's e to the power of half minus 2. That's the value. You could just write it as decimals if you like, but I'll keep the exact value as this. So it's e to the power of 1 plus e to the power of half minus 2. So is this series convergence? Yes. So this is converges to this value. Converges to this value. E plus e power half minus 2. Okay. So no need to worry about expanding a lot. Remember, if the difference is 1, you take the first positive term, the last negative term. If the difference is 2, you take the first two positive terms, the last two negative terms. What do you need to expand? It depends on the difference. So let's see one more. We'll try one additional question, okay? One more about telescoping series. This one again. So firstly, you need to decide. It looks like negative in between. So this is the first thing I need to be careful about. Negative in between. Okay, so it's a good candidate to be telescoping series. The two functions, they are from the same family. Tan inverse, they looks the same. If you look at the in between, so there's the angle k plus 1. So the difference here is only plus 1. The difference is only plus 1. Okay, good. So I need to take what? Only the first term, the last term. So Sn equals sigma from k equals to 1 to n for tan inverse of k minus tan inverse k plus 1. So this is equals to the first term at k equals to 1 only. You need always to be careful about the index, okay? This is important. Not always they start with 1. Sometimes they start with 0 or anything else. So you need always to keep your eye at the index. So you replace according to the first number in the index. Okay, here k starts from 1. So this is tan inverse of 1 minus tan inverse of k plus 1, 1 plus 1, 2. And then you take the last term. You see, I have to add the 3 dots. There's a lot of terms in between. K equals to n. So it's tan inverse n minus tan inverse n plus 1. Let me just make it more clear. So I'll have tan inverse n minus tan inverse n plus 1. Okay, now according to our rule, if the difference is 1, so I know that I'll keep what? The first positive term, this one, and the last negative term, these two only. Okay, perfect. So now this is equals to what? Sn equals the first one, tan inverse 1 minus tan inverse n plus 1. Now I need to take the limit. Limit of Sn as n approaches infinity for tan inverse 1 minus tan inverse n plus 1. Okay, again, direct substitution as usual. So this is equals to tan inverse 1, you can use your calculator. This is clearly pi over 4 minus tan inverse infinity. Remember always the graph of the tan inverse. It's always useful to know the parent graphs. So this is the tan inverse. It looks like, let's use green. So this is the tan inverse. You see, it should remind you of the cubic root. And it has two horizontal asymptotes. This is at pi over 2 and the one down at negative pi over 2. This is x and this is the graph of tan inverse x. Okay, now look at tan inverse infinity. As x approaches to infinity, or here it's n, as n approaches to infinity, the function goes to what? To pi over 2. This is n. N approaches to infinity. So this is minus pi over 2 from the graph. If you do the subtraction here, so this is equals to negative pi over 4. So that means this series, hence the series or the telescoping series converges to negative pi over 4. Okay, hopefully the idea of telescoping series is clear. So I give you the easiest way to do it. You keep your eye always at the difference. This is the easy way to check what will be left. Or else, if you don't like to use the trick, you need to expand a good number of terms till you'll be able to see the pattern. What's remaining, what's cancelling out. Okay? Hopefully this is all clear. Now we need to move to something else after the first type of famous series, which is telescoping series. Now we'll move to another famous series, which we call the geometric series. Okay, so now what do we mean by geometric? Let's first remind you of what do we mean by geometric sequence. Okay, in the school you covered the idea of sequences, and you took two types, arithmetic and geometric. When we say arithmetic sequence, we mean that the difference between the terms is only plus and minus. You add or subtract a value to get the next term. With geometric series or sequence, every time you need to multiply or divide by a specific value to get the next term. So this is the geometric sequence. So if you look here carefully, every time you multiply, if you check these terms, so from 2 to 8, you need to multiply by 4. From 8 to 32 times 4 times 4. So every time you're multiplying by 4, okay, clearly, to go from one term to the next term, every time I should multiply by 4 times 4 times 4. This constant value that I'm multiplying every time is what we call the common ratio for this geometric sequence. So the common ratio, they use usually R to represent it. So the common ratio is, in this case, is equals to R. How can I find it? Either you see what you multiply or you divide any two consecutive terms. So 8 divided by 2, 32 divided by 8. So you notice that it's a constant value and it's always equals to, in this case, it's equals to 4. So this is what we mean by geometric sequence. Now, once we talk about series, then I need to add up these terms. And I need to know the general term for a geometric sequence. So what's the general term? How do they find the general term? The general term, basically, it has two forms. Sometimes they write it, if k starts from 0 to infinity, they write a and k to the power of, or r, we have now the ratio, we used r. So r to the power of k. Okay, this is the general form of the geometric series. So it's a r to the power of k. And we take the summation if k starts from 0. Some other textbook, maybe you'll find them, they change the index. They start from 1. That's why I told you, always keep your eye at the index. Where do they start from? So it should be r. If we re-index this one, so this should be k minus 1. So one of these two forms, they mean the same. Both of them, you see the general term of geometric series. Okay, so now, how can we say or decide whether this geometric series is convergent or divergent? We'll follow this next. This is again another example of geometric sequence. So you ask you, is it a geometric or not? You check the division. What's r in this case? It's 2. Another example, if we say something like this. So clearly every time I'm multiplying by negative 1 over 3. Try to get r, divide any two consecutive terms. You'll find them all equals negative 3. So basically r here equals to negative 1 over 3. And the first number here, you have it. This is important one. We'll use it. This is the first term of this geometric sequence. Now, this is the theorem which tells me when the geometric series is convergent and when it's divergent. And I need you always to remember in this chapter 8, the only series that we guarantee it's converges to what? I know the value is the geometric series. Or else most of the tests coming, they only tell you it's convergent or divergent, but they don't tell you it's converges to what. So the only series that we know is converges to what in advance, if it's convergent, is the geometric series. So this is important to keep in your mind. Telescoping series, yeah, we were able to find to what, but there's no rule. You need to check. For geometric, it's the only one with a rule. Now, how do we see the convergence for geometric series? So they are telling me that the geometric series, see this theorem, it says what? So if you have sigma, this is the general form, as we did in the previous slide. Here they start from 0, the definition. So this is what? This is converges to, you see the rule, we know it's converges to a over 1 minus r. Where do you take a? From here. This is a, the coefficient, the constant term, r to the power of k. R is basically the ratio. It converges to a over 1 minus r when, you see the rule, if the absolute value of r is less than 1. So if the ratio, the absolute value of the ratio less than 1. Basically, what does it mean less than 1? So r is any value between -1 and 1, right? This is how we redefine any absolute value. So r could be half, 1/3, quarter, anything between -1 to 1. Now, elsewhere, if it's greater than or equals to 1, this sequence will be divergence. So now we know the rule for the geometric series. So this is a geometric series. I'll use GS from now on. This is a geometric series. It converges to, you see, we know to what? A over 1 minus r when, if the absolute value of r less than 1. And diverges elsewhere, which is when the absolute value of r greater than or equals to 1. Okay? Sometimes you see the question directly ready in this form, so you use it directly. Sometimes you need just to work a little bit with exponential rules to prepare the question. Basically, what I want you to see all with geometric series, once you see any series looks like exponential function, remember exponential function in general, it's like a to the power of x. So it could be like 2 to the power of 2x, e to the power of x, anything exponential. So any function looks like exponential, it should remind you that this could be a geometric series. Okay, let's see now. So for our first example here, we'll see how can we check whether this geometric series is convergent or divergent. We have it as sigma 5 1 over 3 to the power of k from k equals to 2 to infinity. Now it's clearly fit our general form almost. So this is our general form of geometric series. So this is, I can directly say this is geometric series. Okay, we need firstly to look at the ratio in this case, the common ratio. What's r in this case? So if you think about r in this case, so clearly I have r equals to what? 1 over 3. So is this convergent? Yes. So this geometric series is the absolute value of r equals to 1 over 3, and this is less than 1. So this is converges geometric series. This is the first thing that I can see, just only by looking at r. R is less than 1 over 3, so it's converges geometric series. Now I need to check its converges to what? It's not enough to say it's converges. It's converges, what's my justification? R, or the absolute value for r, is less than 1. Now I need to know its converges to what? So we know the rule. I'll keep it down there to use it. So it's a r to the power of k from k equals to 0 to infinity equals a over 1 minus r. Okay. Now I need to see the index. Look at the index here. It's equals to 2. They didn't start from 0. In this case, if the index is anything other than 0, you have to do it in 2 different methods. In the end, I'll show you the 2 ways and choose whatever is suitable for you. The first method, they do the re-index. They change the index, okay? How do they change the index? We call it re-index. So I start from 0, okay? And then what will be the power? If I start at k equals to 0, let's say that this one, let's think about it as this is, I need to change it from 0. It was 2, I need to go to 0. From 0 to 2, you add 2. So I need the power to be k plus 2. You think how to go back to the original one. You're at 0 now. If you need to go back to 2, you need to change k into k plus 2. So any k here, I need to change it into k plus 2. So now this is the question. Now, the general form has k, not k plus 2. So I need to play around with the exponent rule. So this is equals to sigma. Still now, we change the index from 0 to infinity. and this is 5. I need to expand this. 1 over 3 to the power of 2 for 1 times 1 over 3 to the power of k. Remember, the addition always coming originally from what? Multiplication. So now that's the same. Now compare this to this. You'll notice that this is what should be A, and this is clearly R. So now look here, this is A, this is R, power k, start from 0. So I can say that this is converges to A over 1 minus R, which is equals to, what's A in this case? 5, 1 over 3 squared. 1 minus R, what's R? 1 minus 1 over 3. You can simplify this further. So this is equals to 5 over 9 over 2 over 3, and this is equals to 5 over 9 times 3 over 2, and this is equals 5 over 6 again. So this is equals 5 over 6. Okay, so this geometric series is conversion to 5 over 6. Now again, what I did here, what I did is what we call re-index. I've changed the index. The index was 2, I need it to be 0 according to the general form. Now think what happened here when you changed. Now you want it to be 0, it was 2. From 0 to 2 you think backward. From 0 to 2 you have to add 2. So I add to k to the exponent, or any k in this inside here in ak, I make it k plus 2. So now the general form is k, not k plus 2. So I need to expand it this way. I needed k. So by this, I managed to write it in this form. Now the other way you could do it, I told you, there's two methods. Either you do the re-index, or the second way you can do it, which is easier. I think this is much easier, but it's good to understand how to do the re-index. You need it later on in any coming math courses. If there's sigma, like differential equations, you need to know how to deal with the sigma notation, how to do the re-index. The second method, you need to find what's the, we need to make A as the first term. I need A as the first term in this time, as the first term. How do I find A as a first term? I'll call it A1. So I need to expand the series. So this series from 5, 1 over k, it starts from 2. So try to expand. So this is 1 over 3 squared plus 5, 1 over 3 to the power of 3, and the list goes on. So now what's A1, the first term in this case? It's 5, 1 over 3 squared. What's R in this case? Clearly, it's 1 over 3. So this is converges to A1 over 1 minus R, and it's the same value like here, 5 over 6. So this is easy way, but the only mistake I see as a common mistake with the students when they solve using this method, if they do it from them without considering that A should be the first term, you have to expand to see the first term. This is your first term, or else you'll do it wrong. What's happening in the exam usually, they don't look at the index and they take always A as 5. So it will not be correct. If you need to avoid doing the re-index, you need to check what's the first term. So you need to use always A as the first term, not the number, look here, 5. So I can't use A as 5 always. If the index is other than 0, I need to check what's the first term. Just only expand, try to replace the first value. K equals to 2, so the first term is 5 times 1 over 3 squared. Okay, so this is, with this method, you need to be careful about the first term, or else use the re-index. It's up to you. Now let's try one more. Okay, this one. This is example 2.5. I need to investigate, same thing, the convergence or divergence of this series. Firstly, always when you see any question with series, especially later on when you learn many different types of series, you need to check Okay, this series looks like exponential function. And anytime I see something like exponential, I need to think about geometric series. So this is basically a geometric series. Okay, what should act here like R? If you think about R, the ratio of this geometric series, it's -7/2. And now consider what's the absolute value for R? It's 7/2. Now think, is it less than 1 or greater than 1? This is equal 3.5, so this is clearly greater than 1. So is this geometric series convergent or divergent? Remember, geometric series convergent if R, or the absolute value for R, less than 1. But here greater than 1, so this is divergent. So hence, it's, or the series, the geometric series diverges. Okay, why? Because the absolute value of R greater than 1. Okay, do I need to check further? Do I need to find what's A over 1 minus R? For sure, no need. If it's divergent, that's it, full stop, finish. No need to continue. Okay, now let's move ahead. Now we know what two famous series. So in this chapter, you need to learn just to have a bank of series and bank of tests. So now I know two famous series, telescoping series, I know geometric series. You have to keep this in your head always when you look at any coming series. Now we need to prepare for our first test. We need to prepare for our first test. Now see this interesting theorem. This is really useful one. It says that if the sigma of AK from k equals to 1 to infinity. By the way, this is something useful you need always to keep in your head. The index doesn't change if it's convergent or divergent. It's only changed the summation. So this theorem, if I say k equals to 0, k equals to 3, from any number you start, it doesn't change whether it's convergent or divergent, okay? This is important to understand. So convergent or divergent, it's not related to from where you begin. So if it's k equals to 1, but I make it k equals to 3, it's still convergent, okay? It's only changing the summation, but it doesn't change if it's convergent or divergent. Okay, let's go back to the theorem now. If sigma ak from k equals to 1 to infinity converges, then the limit for the sequence inside ak as k approaches to infinity equals to 0. Okay, so this theorem says that if the sigma of AK as a series, okay, I'm thinking about the series. If this series converges, then the limit for the sequence, remember AK is the sequence and the summation is the series. Once we add the sequence term, we call it series. Then the limit for AK is equals to 0 as k approaches to infinity. Okay, how can this be useful? Now I need you to think a little bit. We need to use our knowledge about logical statement. So if A, let's say this statement is A. So if A implies B, this is what we have. It's one way, only if then. Does it mean that B implies A? What do you think? So you think if the limit of AK equals to 0, does it mean that the series converges? If the limit 0, do we get that it's convergent? No, not necessary. So always if the theorem is only if then, so it's like only one way, one direction. If A, then B. But does it mean that B implies A? No, it doesn't. But what can we guarantee with this logical statement? If A implies B, it's always true that not B implies not A. This notation, I don't know if you saw it before or not, but this is what we say not B, the negation for B. Not B implies not A. Okay, let's think about this theorem. What does it mean not B? If the limit equals to 0, what should be not B? the limit, okay, let's say it this way. So if limit of AK does not equal to 0, so what does that supposed to mean? Then sigma AK from K equals to 1 to infinity. What's the negation for convergence? What's the not convergence? It's divergence. And this what takes us, this theorem, to our next slide, which is the first divergent test. So if the limit of AK does not equal to 0, we can 100% guarantee that the series diverges. You see from where they got it? Just it's like basic logic. I need you always to remember these three statements. A implies B, it doesn't mean that B implies A, but always the negation is true. So not B implies not A. Now see this next test. This is what we call the kth test of divergent. Many books, they call it divergent test. Divergent test. You can use any name you like. You call it divergent, kth test, it's the same. So what does the test say? Just as we saw before. If the limit of AK does not equal to 0, then the series diverges. This is really interesting test, and it should be always your first test to check. But you need to be careful about the common mistake again. So if the limit equals to 0, it means nothing. Okay, if the limit equals to 0, like it's B, it doesn't mean it's converges. So let's agree on this. When this test is useful, only if the limit of AK does not equal to 0. If the limit of AK equals to 0, there's no conclusion. You need to try another test. Okay, so if the limit of AK equals to 0, we have no conclusion. Try another test. So there's no conclusion. Remember, please. Let's try one simple example using this test, which should be always your first test to check. Okay, so what's your first test always? Divergent test. See now this question. We saw this. It's false if you go backward. Now we'll try something like this. I need to check the convergence or divergence for K over K plus 1. Now, the first thing I need to look at AK. It's K over K plus 1. Now think, is it one of the famous series that we already know? Is it telescopic series? No. There's nothing to do as partial fractions. Is it geometric series? No. It doesn't look like exponential function. So I need to apply the first test we know. I'll check the limit for AK. As K approaches to infinity. So the limit for K over K plus 1 as K approaches to infinity. If you check direct substitution, it will give you infinity over infinity directly. Okay, so now if I think how to find this limit, you could use L'Hopital rule. But remember here K is integer, so I could use X. So I could say that f of X equals X over X plus 1. So the limit for X over X plus 1 equals, if you use L'Hopital rule, this is X. With L'Hopital rule, clearly the limit will be equals to 1. So this limit here equals to 1. So the limit for AK equals to 1 as K approaches to infinity. If the limit of AK equals to 1, which does not equal to 0, so we can say that hence the series diverges by the kth test. The kth test. I need you from now on, any test you use, you have to write it down. So you need to justify your answer. How did you conclude that this is equals to, this is convergent or divergent? What test did you use? So here it's divergence by what? By the kth test, by the divergent test. Since the limit does not equal to 0. the limit here does not equal to 0, which is, if you go back here, this is the divergence test. Limit does not equal to 0, directly you say it's divergent. Okay, by the way, here using x for now, since from 8.1 you know that we should replace k as it's not differentiable, we use x. But later on you'll be allowed just to use it directly as L'Hopital rule. But now I needed just to use with x, just since we're still dealing after section 8.1. So we know I use the corresponding function to show the limit equals to 1. Okay, so this is a question on the curve test. Clearly, if I graph this series, clearly that it keeps getting larger, larger, larger without a bound. So this is divergent. Now there's one interesting theorem for us. Sometimes we don't have one series only, and there's a relation in between, like you add two series or you subtract. So how to deal with these cases? If I have like sigma AK plus or minus BK, how do I consider their convergent or divergent? So how do I deal with this case? If it's summation or subtraction, if the first one converges to A, let's say, and the second one converges, then the overall will be converges to A plus B. So if both of them converges, then the overall should be what? Converges as well. So if I have convergence series, let's just make it in summary. So if I have converges plus or minus converges, the result will be what? Converges. To what? This value. If it's to A, to B, then you add or subtract the overall result. Now, if the difference is only constant term, like this, CAK, the constant doesn't change the convergent or divergent, because you know you can take it always outside of the sigma notation. So if I have like sigma A, or let's say C, AK from K equals to 1 to infinity, I could always take this C outside. It's a constant, it's not related to the index. And this one, if it's converges to A, let's say, so the overall will be converges to what? CA. So the constant doesn't change anything. Now the next part of the theorem, which is interesting, this one, if I have one of them convergent and the other one divergent, the overall should be what? Divergent. So if one of them convergent and the other one divergent, the overall is divergent. Okay, let's see how can we write this result. So if one convergent plus or minus divergent, the result will be divergent. It will give divergent. Okay, now what's the case we missed? If both of them divergent, what do you think the result will be? If both of them divergent, the question now, can I guarantee that the result is divergent? Or is it convergent? What do you think? If both of them divergent, let's see the next note, which is really important. If both of them divergent, it does not mean that the result is divergent. Okay? So it's possible that maybe both of them divergent, but the addition or subtraction, especially with that telescoping series, we'll see this in a bit. So it could be that their addition or subtraction may be convergence. So no guarantee. Okay? So this is the first note. So if it's divergent plus or minus divergent, it should not be the result divergent. We don't know. Maybe it's divergent, maybe it's convergent. You can't guarantee. But it does not implement that it's 100% divergent. You need to check. Okay, so nothing says that their addition is divergent. Okay, the next quotient rule you need to be aware of, that the sigma, we saw the sigma before in this theorem, that we could distribute the sigma over the addition and subtraction. But you need to be careful that the sigma notation, there is nothing to say that we can distribute the sigma over the multiplication, okay? So if it's multiplication, I need to deal with them as a whole together. I can't split the question. I can't split the question. So something like this, let's say sigma, you have 1 over 3 to the power of k times k over k plus 1. And the relation is times. I can't say this is the first one is geometric, the second one is telescoping, and you deal with them separately. No, you can't. It's multiplication. Okay? Now we have one last famous series, and then we're done for this section. This last series is very famous series. We call it the harmonic series. And this series is basically coming the name from music. So just like if we think about this sigma notation, so this is like if you expand, this is 1 plus 1 over half plus 1 over 3, 1 over 4. So just like you're adding the reciprocal numbers, the reciprocal of integers, which is 1, 2, 3, 4, you add up their reciprocals. So this is what we call harmonic series. Now, if I think about this series, if it's convergent or divergent, there's many different proof for this, that it's divergent. We'll show in a bit that this is divergent. But the interesting part about the harmonic series is that it's divergent, but they call it slowly divergent. So maybe you think here the number is getting smaller. Every time you add, it's a smaller number. That's why it's getting, okay, it's decreasing, but it's add up to infinity. So in general, but slowly divergent, it's just not easy to see that the numbers are getting smaller. So what they call it slowly divergent. So this is divergent. So anytime I see 1 over k, I know directly it's a harmonic series and it's divergent series. Regarding the proof, in this course, it's not required from you to do the proof, but it's good to see the idea of the harmonic series. So directly I know 1 over k, it's divergent. How do you justify your answer? You say it's divergent harmonic series. Now the proof basically, if you look first to check the first test, remember we said always when we check the first test, the kth test. Try with the kth test. It's equals to 0. So does it mean it's convergent? No, it doesn't. So if it's equals to 0, then I don't know. Maybe it's convergent, maybe it's not. Now the proof depends on this idea. It's interesting to see the proof, but it's not required from you. I'm not going to ask you the proof in the exam. But the idea depends on this. So if we think about this 1k, if I have the summation, so just like you're adding rectangles with width of 1, okay? And the length should be 1 over k. So notice the first rectangle with the length 1, the next one it's half, the one after 1 over 3, and then 1 over 4, and then they keep getting smaller rectangles. And they compare it with 1 over x, which is, we know the graph for positive x. This is the 1 over x for positive x. It goes this way. Now, if we compare the area under the curve 1 over x with the summation of these areas, clearly the summation of the rectangle areas is bigger. It goes above this curve. So if I think about this summation in this way, so I say at the sum of the areas of the rectangles, the n rectangles, it's greater than or equals the area under the curve. And how do we represent the area under the curve? This is one of the applications for the integration. So the integration from 1, this is we start from n, the last one is n plus 1. So the integration from 1 to n plus 1 for 1 over x is what actually represents the area under this curve. Try to find this integration. So the integration for 1 over x is ln x, replace from 1 to over n plus 1. This is ln n plus 1. Okay, so ln n plus 1 as n approaches to infinity, this is improper integral, by the way. So as n approaches to infinity, it's diverges. And from the comparison test, this is larger than a divergent one. So for sure, the summation of the areas of the rectangles is divergence, which is the harmonic series. So this is one of the proof that they use to show that the harmonic series is divergence. Okay, and the harmonic series is a good example to show that if the limit of 1 over k equals to 0, but yet as a series it's divergence. Okay, clear? Now I'll use the idea of the harmonic series to show you a counter example. So you see the harmonic series is a good counter example for more than one thing. If I need to go back to this case, okay, the harmonic series, this result, the divergent. Remember when we covered the first question about the telescoping series, it was sigma, if you remember, it was 1 over k minus 1 over k plus 1. This is the first question we did as a harmonic series, as a telescoping series, sorry. And we showed that this one was convergent. We saw that this is a telescoping series and it was convergent, this one. It's a telescoping, convergent, telescoping series. But if you think now at what we have here, 1 over k is a harmonic series, it's divergent. And this one is what we'll, from now on, we'll use later on a way to prove it. But for now, anything looks like this, like 1 over linear combination, AK plus B. This is divergent. And this looks like harmonic series or similar, looks like harmonic series. Later on, when we take more tests, I'll show you how to prove that this is divergent, but it looks like harmonic series. So now I know that these two, this is divergent, and yet their subtraction was convergent. So this is a good counter example to show that divergent plus minus divergent, it doesn't mean divergent, okay? Now what we have next, it's just only a few exercises to practice, okay? So this is the first one. You need to try with this one. You can pause the video, try to solve it yourself. Remember, first thing, you look at the question. It should remind you of something. This should remind you of which series. This is exponential, so it's similar to geometric series. So first thing, I see that this is geometric series, but I need to see what's R in this case. You have two ways to do it. Notice the index start from 2. Now, if I think about this one, let's try to simplify a little bit the powers here. So this is sigma from n equals to 2 to infinity 3 to the power of n plus 1 times 2, 1 minus 2n. And this is equals to. Let's prepare a little bit with the index here. So this is 3 to the power of n times 3 to the power of 1. This is 2 to the power of 1. 2 to the power of 1 over 2 to the power of 2n, right? From n equals to 2 to infinity. And this one, I could write it as sigma. I'll take the one without n. 3 times 2, 6. And the one with n, I could combine them with n. So this is a 3 down. You took n, so you have 2 left. So this is 2, 2 squared. So this is 4. From n equals to 2 to infinity. Now, I'm not going to do the re-index, okay? I'll use it directly. So if you need to do the re-index, this is equals to what? Sigma 6, 3 over 4. Now it's n, but I need it to be 0. So from 0 to 2, it's 2 the difference. So I need to add 2 to the power. Okay, this is how I do re-index if I need to. But no need to do the re-index. I know I need to do it directly from here. So what should be the first term, A1? Check what's A1, the first term. Try with n equals to 2. So this is 6, 3 over 4 squared. This is the first term. What's R in this case? 3 over 4. Is it converges? This is less than 1, so this is converges. Converges geometric series. Okay. Converges geometric series. Great. Now, how do I find converges to what? It's converges to. A1, the first term, 1 minus r. Try. This is 6, 3 over 4 squared divided by 1 minus 3 over 4. If you use your calculator directly, it will be 27 over 2, which is B. Which is B. I need to see we're not going to ask any multiple choice questions, you know. That's why I need to show the steps, what I'm doing. This step, the re-index, it's optional. So either you use this one, the re-index, and then you expand this, power n, power 2. So if I need to do the one extra step from here, the next step should be equals 6, 3 over 4 squared, 3 over 4 to the power of n, okay? And now this is similar to the general form. This is A, and this is R. So it's up to you. Either you do this, or else you have to use A1 as the first term. So you need to check what's the first term when you replace n equals to 2. Okay, so this is the first question about geometric series. Now one more. Something like this. Sometimes it doesn't look straightforward as geometric series, so it has like some additional steps. So this looks like directly, it doesn't look like straightforward, but I see that this is exponential function. Anything exponential, it should come to my head, the geometric series. Now the index here is 0, so no need to worry about the index. So I need to play around a little bit with the question, with the exponent. Let's prepare them separately without the summation. 1 minus 2n over radical 2 to the power of 2 minus 2n. This is equals to. So this one equals e to the power of 1 times e to the power of negative 2n. Down, radical 2 squared times radical 2 to the power of negative 2n. Okay, good. Anything without n, I could just combine them as a constant term. So this is equals e to the power of 2. Now these two, I could write them as e to the power of radical 2 to the power of negative 2n. Okay, I could combine them with the same power. Remember, if you have a over b to the power of n, you could easily write them as a over n, b over n. This is the rule I'm using. Now remember, we need n, not 2n or negative 2n. How can I deal with this? I'll use the exponent rule. So I'll use a to the power of n to the power of m. This is equals to what? A mn, right? Power to a power, you multiply. So this can be easily seen as e to the power of 2 something to the power of n. So what do I have left inside? Power negative 2 squared, but it's negative, so I could flip them. So this is 2 over e squared. Okay, clear how I did it? So this is, I'll show you here. It's e over radical 2 to the power of negative 2n. This is e over radical 2 to the power of negative 2 to the power of n. And this is squared but negative, so I could take the reciprocal. Radical 2 squared, it's 2. E to the power of 2, it's e squared, all to the power of n. Okay, since the power is negative, so it's the reciprocal. Okay, now the question is ready. So now the series equal to what? The question equals sigma for e over 2 over e squared to the power of n, from n equals to 0 to infinity. So what's a in this case? E over 2. What's r? 2 over e squared. Notice that r here is less than 1. So this is convergence. This is convergence geometric series. Now I need to find convergence to what? Convergence to e over 2 divided by 1 minus 2 over e squared. This is complex fraction. You can simplify it always by doing what? Multiply by the LCD for all. What's the LCD for all of them? 2e squared. Down 2e squared. Here the denominator 2, down e squared. The common LCD for all of them, 2e squared. So this is equals to, in the numerator it's 2, we cancel 2 with 2, so you end up with e power 3. Down, distribute this. This is e squared minus 4. So compare, this is part A. I know with multiple choice it's easier. You could expand the first two terms. You find what's A1, A2, divide them, R equals A2 over A1, and you know what's A1, how to apply. And this is R. I know you could do this directly as a multiple choice question. This is easy. But again, I don't usually ask multiple choice questions. So you need to know how to manipulate with exponential function, how to write it this way, okay? So if the question is multiple choice, it's easy task. You can do it fast. One extra question, last example we have, as you need to try it yourself. Please, for any of these questions, your turn. Try always to pause the video, try it yourself, okay? Now this is like an exam style questions. We need to determine whether these series are convergence or divergence. If convergence, find its value. This part of the question always, if it says find its value, so you need to know that this is one of the series that you can find its convergence to what. So it could be telescoping or geometric, by the way. This is the only two series that we can find its convergence to what. So anytime I see find its value, so it should come to my head either geometric series or telescoping series. Now this question here, if you look at the question, it looks like exponential function, okay? There's addition. So I could expand it into two questions. So this is 1 over 3 to the power of n plus sigma 2 over 3 to the power of n. From n equals to 1 to infinity, n equals to 1 to infinity. So this is basically a summation of two geometric series. This first one is convergence. Why? Because r is less than 1, the absolute value for r. Same here, it's convergence. So how can I find the summation? Remember, I'll use a over 1 minus r. So for the first one, what's a? Try a at, when you try to find a, this is n started from 1. A is the first term. I need you always to check what's the first term. So if it's 1, this is 1 over 3. Down 1 minus, what's r in this case? 1 over 3. Plus, here, check 1, 2 over 3 power 1. First term is 2 over 3. Divided by 1 minus 2 over 3. And you have a calculator. You can check it's equals to what by yourself. Okay, so the idea is just to distribute the summation, plus, plus. Both of them geometric series, both of them convergence. So the total or the overall is convergent. This next one looks like two style of series. So the first one, if I distribute the summation, this is 1 over e to the power of n plus sigma 1 over n, n plus 1. N equals to 1 to infinity. Same thing here. This first series, if you check, this is clearly a geometric series. This is a convergence. This is a convergence geometric series. It's 1 over e, the absolute value less than 1. This one, what do you think is this one is? This is our first question we did today, first example, about the telescoping series. This is telescoping series. And we show that this one, it was convergence to, I guess, how much was this one? You can check. So this is a telescoping series. So I need to do these questions separately. So you deal with the first one alone. You deal with the second one alone, and then you add up the result. This one converges to what? This one converges to what? Okay? So that's all about 8.2. I did honestly like modify the PowerPoint. I added a lot of extra questions, a bit extra about telescoping series, more of the questions to try it yourself. Because I need you to practice more, okay? And it's a video, we can take our time. Unlike sometime in the class, we can do like a lot of extra questions. Okay, hopefully you like this section. Next time we'll be doing section 8.3 and you will learn three important tests that we can use for convergence. Take care and see you next time.